Welcome to this lecture. We are in lecture number 14 now, and in this lecture we will talk about we will solve some problems, and then we will talk about some more about we'll talk some more about transformer losses. So we have to find the no load current of a 400 volt 50 hertz single phase core type transformer. We are given that the mean length of magnetic path is 200 centimeter. The gross core section is 100 centimeter square. The joints are equivalent to 0.01 mm, which is the air gap equivalence. The magnetic flux density is 0.7 Tesla. The core loss is specific core loss is 0.5 watts per kg at 550 hertz and 0.7 Tesla. And the ampere turns are 2.2 per centimeter. The stacking factor is K 0.9, and the density of steel is 7.5 into 10 to the power 3 kilogram per meter cube. So to proceed, before we proceed ahead, I would like you to pause this video and try to solve this question on your own. And if you are not able to solve it, or you have solved it and you want some clarification, you can then proceed to watching the video. So here, the first step that we do here is we calculate the total MMF, the total magnetic motive force, and as we discussed in the last class, it is denoted by AT0, and it is a sum of 2 ATI Li plus 2 ATY Ly plus the MMF for joints. Right, so this can be further written as plus B by mu naught into length of path. So this comes out to be, this is 2.2, the ampere turns, into 200, where 200 is the length of path, plus we have this is 800,000 times 0.7, where and then this is B, and this is 0.7, and the next is you have the path length is for the air gap, it is 0.1 mm, 0.01 mm, so it is 0.1, this is 0.1 into 10 to the power minus 3. So if you take the total value of this, you come out with the ampere turns, that is equal to 496. This is the total ampere turns. Okay, so what is added here, we are given in this the ampere turns, this is the total ampere turns minus the air gap. So to this we have to add this factor which we discussed in the last class. So ampere turns is 496. Now we know that we are given the gross iron area. The gross iron area is 100 centimeter square. So to calculate the net iron area, AI, we calculate that by using the gross iron area into the stacking factor. So this is 100 into 0.9, and since this is centimeter square, we convert it into meter square. So this is 90 into 10 to the power minus 4 meter square. This is AI, the net iron area. Then the EMF per phase, since this is a single phase, so it's the same, it is 4.44 FBM, AI, and TPH. So this is given to us to be equal to 400 volts. So this is 400. So here we calculate the turns per phase. So that is 400 divided by 4.44 divided by 50.7 into 90 into 10 to the power minus 4. So we get the turns to be equal to 286. Then the magnetizing current, IM, the RMS value is ampere turns total MMF divided by root 2 times TPH. So that is 496 divided by root 2 times 286. So this is 1.226 amperes. So this is magnetizing current, IM. Now another point to note here is that this specific core loss is given as 0.5 watts per kg. So we have to find the weight of the core, and to find the weight of the core, we see the volume of the core, and we multiply it by density, right? So this is volume of the core you get by net core section into length into density of steel. So this is 90 into 10 to the power minus 4 into 2 into 7.5 into 10 to the power 3. So this comes out to be 135 kg total weight of the core. So total core loss comes out to be the specific loss into the weight of the core. So this is 0.5 times 135. So this comes out to be 67.5 watts. Then the core loss current, IC, is 67.5 divided by the voltage, that is 400. So this comes out to be 0.168 amperes. And when you know the magnetizing current IM and IC, you can get the no load current, I naught, and that is the phasor sum of the two currents. And when you sum up these, you get the no load current to be equal to 1.237 amperes. So this was one example of the calculation of the no load current in terms of the losses. I encourage you to solve some more problems. I have both solved and unsolved, so that you are able to better understand this, and that will help you in practicing this by practicing this, factoring in the losses into the design process. Now moving on, we will now talk about transformer losses. And in the transformer losses, we will see how the design parameters influence the losses of the transformer. So the first thing that you have to keep in mind is that these losses are can be divided into two parts. This is the no load losses and the on load losses. So first, when we talk about no load losses, this is these losses, as we discussed in the last class, these occur in the core of the transformer, and these losses occur every time the primary is energized, every time the primary winding is energized. So in case when the primary is energized, the I square R losses are considered to be negligible, and you must be aware that this I square R loss are also known as the copper losses. So in case of no load, the copper losses are considered negligible. The core loss, which is the no load loss or other name for the no load loss, core loss, has two components. It is the hysteresis loss, and the other is the eddy current loss. Now, for hysteresis loss, hysteresis is due to the magnetization and the demagnetization of the core. We have discussed it in the beginning that this cycle leads to the formation of a hysteresis loop in the curve, right? So this loss, the hysteresis loss, you would have studied this in your machines course as well. This loss is quantified as it is Kh, the hysteresis loss constant, and this depends on the nature of the material used, and it is proportional to the flux density raised to the power of 1.6. Okay, and it is also proportional to the voltage and the frequency. So this is hysteresis loss, Ph. The second type of loss, is the eddy current loss. This occurs because alternating current is introduced. So what happens when the this alternating current leads to production of alternating magnetic field? Eddy currents are introduced into the core. You know this concept of eddy current. This is not new to you, and you also know that to reduce this eddy current loss, you have the core is laminated. It is laminated into thin sheets, right? And these thin sheets are insulated from one another, right? So this loss, the eddy current loss, PE, is quantified as KE V BM square F square and T square, where Ke is the constant and depends on the material or resistivity of the material. V is the voltage, Bm is the magnetic field, magnetic flux density, F is the frequency, and T is the thickness of the laminations. Right? So the higher the thicker the laminations, the more the eddy current loss is going to be. So this was all about no load losses or the core losses. We then talk about part B is the copper losses, which is also the on-load losses. The copper losses is the loss that occurs in the winding when there is load connected at the end. Okay, so this is known. So based on the value of the current, you can calculate this as I square R. Fine. So for the core loss, in the previous question, in the question that we solved, this core loss has two components. It has the core loss in the legs and the core loss in the yokes, right? So what we do to solve this, how do we obtain this core loss? We basically see the core loss in the legs, loss per kg times weight of leg, right? So this can also be found out by loss per kg times volume of leg into density of steel, right? So the total core loss is equal to the number of legs into loss per kg per leg into volume into density, right? This is the total core loss in the legs, and then you have the core loss in the yoke. Well, how do you calculate that? You'd say the loss per kg times the weight of yoke. Here again, weight of the yoke, you can simplify. You can say that the core loss in the yoke is right. So the density of the iron or steel used is about 7.55 to 7.8 gram per centimeter cube. So this is how the core losses are computed. And for the copper losses, I've told you, you see the current and then multiply it, square it, and then multiply it with the resistance, and then you can calculate the copper losses. Fine. So this was all about a brief summary about the losses present in the any typical transformer. So now, concluding this section on losses, let's see what happens when we change the frequency. When you change the frequency, what happens? The losses change. Since in every loss the term is dependent on the frequency, so when you change the frequency, the losses change. So let's see what happens. Let's see the effect on core loss. So what is the effect on core loss? We know that this the EMF is equal to 4.44 FBM AINT, and the eddy current loss is equal to KE F square BM square, right? If you keep this voltage constant, E, if it's kept constant, then the term F into B is constant. You can see it here. If you have E constant, then this F into B product is constant. So the eddy current loss will remain constant as long as this E is kept constant, so as long as E is constant, the factor F into Bm is constant. So what happens? Because if you see frequency and Bm, they are together a product. The product is constant. So even if you change frequency, the eddy current is this factor is going to be constant even if you change frequency. So the eddy current loss is going to be the same, provided E is kept constant. Okay, but the hysteresis loss, where this H is KH times FBmx. This x I introduced earlier, it's around 1.6. So here to this x can take the value from 1.6 to 2.2. So depending on the nature of the magnetic material, the hysteresis loss takes the following form. So if you have x to be equal to 2, what happens to this term? pH becomes kh times FBm into Bm. So again, this F times Bm is a constant, where we assumed this EMF to be constant. So we can say that this is constant K and this is Bm, right? So we say since E is constant, F into B is equal to K. So what happens here? Then you can say that this KH times K by F. So you get this frequency term in the denominator. So what happens to the hysteresis loss? The hysteresis loss is inversely proportional to the frequency. If the hysteresis loss, the hysteresis loss is inversely related to the frequency. Why is this so? Because you have said that the product, this F into B, is a constant. So if you have this product constant, you replace it by this factor K, and this you can replace by obtain the because Bm is inversely related to the frequency, so hysteresis loss comes out to be inversely related to the frequency, right? Provided E is kept constant. This is important. Okay. The second factor that is to be checked and seen is the effect on winding resistance. Effect on winding resistance. What happens? When the frequency changes, the resistance, because resistance increases, the resistance changes due to the skin effect. When the frequencies increase, what happens? Because of skin effect, the current is restricted to the edge of the conductor only. You have studied skin effect. So what happens? The area of the cross section of the conductor gets reduced, and by means of that, the resistance increases. So when you have the frequency increasing, the winding resistance increases. Okay, and however this is small. If frequency rise is small, the change in resistance delta R is negligible. This is understood that if there is a very small increase in the frequency, then the change in resistance is not much, but if there is a significant increase in the frequency, the winding resistance increases significantly. Point 3 is the effect on leakage reactance. So you know that the leakage reactance X is equal to 2 pi FL. So if you increase frequency, the leakage reactance is also going to increase. This is simple. And what about voltage? Lastly, what about voltage? If you change along with frequency, if you change the flux density B as well, a new voltage rating is possible. Because what happens if you increase frequency alone, the voltage can be increased further if you change this B. So you can have a higher operating voltage for the transformer. But for this new voltage rating, what is required? The iron loss and the no load current has to be recalculated. Okay, so this is some brief about the effect of this frequency on the different types of losses and different types of transformer parameters. I hope this is clear. And with this, we almost come to the end of the this unit on transformer design. Now, two topics remain. One is the cooling of the transformer, and the next topic is the design of tank with tubes. If we get time at the end of the course, if we get some time, we will do these two topics later on. But for the time being, you can skip these topics. Those of you who are interested can read them at their own places. But for now, we will end this unit on transformer design. We will, if we get time, I'm repeating once again, if we get time at the end of the course, we will touch these topics, that is the cooling of the transformer and the design of tanks with tubes. And with this, we come to the end of this unit on transformer design. The next unit we will start in the next lecture, and by that time I hope you will revise all of this, whatever we've studied so far, and also see some more problems. And I'll see you in the next lecture. Thank you.